We present a neural scene graph, a controllable representation of scenes with elements that are learned from data. The graph consists of objects and material representations that are extracted from data and stored as vectors. Each canonical geometry has its own representation, as does every material type. Here, we see a scene made of 3 different objects and 4 materials. The vector representations are shown above. Each representation can be transformed using familiar editing operations that are encoded and stored as high-dimensional matrices. For example, we can deform and translate the teapot geometry and adjust the base color of the material. Each representation can undergo a different chain of transformations. In this case, the entire scene is transformed using the top-level transformation, which represents the root node of the graph. In order to render the scene graph, we collapse it into a stream of objects for rendering. We render the stream using a recurrent neural network. The geometry vector is concatenated with a material vector and then input into the recurrent blocks. The recurrent block processes the input vector and modifies the internal state of the block. We continue this process with the other objects in the stream until all of them are processed. Then, the final internal state is passed through a pixel generator to produce the output image. Here, you can see some examples of training data used for one of our models. We train on random scenes containing up to 4 objects with different materials and transformations. We show a user interactively building a scene using a model trained on the previously shown data. The output images from the neural renderer are shown online as adjustments are being made. We can change the object's transformations and adjust the color and material, and even add new objects, as you can with traditional methods. This video shows a 2D animation produced by our model. The model was trained on random scenes consisting of up to 4 randomly transformed and colored shapes. The animation is temporally stable and even contains a non-linear deformation. This model was trained using 16 alpha mask textures to allow producing sprite-based 2D animations. Here, we show a 3D animation rendered by our model where 2 tori play volleyball until the ball passes through the right torus. And the tori have a solid appearance and the ball is volumetric. Now, we just swap the material representations between the sphere and the tori to make the sphere solid and the tori volumetric. Here we show a turntable animation of a head consisting of 250 cylinders. The model can render this scene with some inaccuracies, even though it only saw scenes with up to 4 objects during training. The results are not perfect, but the scalability shows a great promise for developing our method further. And finally, here is another interactive session where our user is building a scene from scratch with a different model that allows bending 3D objects. Thank you for watching.